we will take up this analysis of plane truss by stiffness method. So first let us spend some time on the analysis of this truss. Already you know by definition what is a truss, plane truss. Plane truss is nothing but a structure which is again made out of by only one-dimensional elements or lying elements which are all lying in one plane and are interconnected by pin joint, not rigid joint. It is connected by pin joint, all lies in one plane. And also another assumption is these members, all line elements, they are arranged in the form of triangles. That is why very important in a truss. The arrangement of all the members will be in the form of truss only, number of truss. So that means when it is arranged in the triangles, when it is arranged in the form of triangles, all members you cannot expect to lie in orthogonal direction. You cannot expect, as in the case of beams or rigid orthogonal frames. In the case of beams, naturally all members should lie, or all the elements should lie along a line. In case of orthogonal rigid frames, all members should lie either along the vertical line, vertical axis, or horizontal axis. The both horizontal and vertical axis of the members, they are coinciding with the global coordinates. Whereas here in truss, you cannot expect, because the truss is an arrangement of all these line elements in the form of triangles. The moment I say triangle, the arrangement of the elements should have inclined line. So whenever members are inclined, then we cannot adopt this system approach for hand computation. We have to go for this element approach of analysis only, the element approach. That is the basic difference between beams and our rigid frame analysis by system approach. System approach directly we cannot apply to plane truss, we have to go for element approach. That means element approach means we have to clearly define what is member element axis or member axis, what is global axis, and first all the loads we have to take, and also element properties we have to determine with respect to element axis or member axis, and evaluate the displacements on account of the load. Load also we consider in global axis. We determine the global displacement using that force displacement relationship P is equal to KD, where that K stiffness matrix also should be in the global coordinates. We have to determine stiffness matrix in terms of global coordinates. Though we determine that stiffness matrix in terms of member properties, locally we have to determine, we have to convert that into global. Whereas in the earlier problems, we didn't have problem because global and local, they were coinciding. Whatever stiffness matrix we were generating, they were all same for local as well as global. We didn't have any problem. But here, we had to determine global stiffness matrix separately, member stiffness matrix separately, and we had to find out a relationship between the global and local stiffness matrices through what is known as transformation matrix. Again, the transformation matrix is in the form of geometrical properties like your direction cosines, L and M. That is whatever the member inclination which is there in the plane. So that depending upon that member inclination, we have to find out direction cosines and we have to evaluate the global stiffness matrix in terms of that. Having known that global stiffness matrix, knowing the external load, we have to arrive at the global displacements at various joints and then find the element forces using, again, same displacement force relationship using member stiffness matrix locally after converting the global displacement into member displacement. So that is the extra exercise we have here. First we have to find element properties, then we have to transform all them into global properties, then evaluate the unknown displacements in terms of global axis, then again come back to local member stiffness properties, and we have to evaluate the member forces. So now we will take up a typical truss line member. So I will just consider a typical truss element, plain truss element. So it will have two ends. The end, one end we call it as J end or near end. So another end we call it as J end or far end. So there will be two ends, near end and far end. So you can choose whichever the end as near or whichever is the end as far end. It depends purely on the individual. So there is no definite rule attached for assigning near end and far end. It purely depends upon the individual. Having assigned that near and far end of a particular member, the near end to far end line, if you move in that direction, that will be called as the member axis. That is one of the coordinate axes. That is called the member or local axis. Other two orthogonal axes to this, we treat other two axes either in this direction as y or down as y, and of course since it is a plane frame, normal to this plane, that is z axis, that is not changed always. And here having defined that, and the force in this particular plane truss is always axial force. That means force will be through the axis of the member. So this is, and also displacement also has to be through the axis at the ends, and this displacement coordinate we call it as 1 and this as 2. The positive direction, coordinate is the word I have used. Coordinate means it is indicates the positive direction of either force or displacement. Positive direction of displacement will be along this line, that is in this direction, whatever I have shown here. In the direction of one, positive direction of displacement as well as force. Here at this far end, this is the direction, same direction. Then member force, we can determine outwards. For equilibrium, it should be equal and opposite. Here also, it should be equal and opposite. Then we can say whether it is in compression or tension. That during the analysis that we will see how to find out the actual member forces. Now first let us take the local or member axis of a plane truss element JK. The member, we can call it as I member, and the coordinate of this near end and far end with respect to the global coordinate axis we can find out. You choose the global axis also. The near end and far end coordinates we can define like this with respect to the global coordinates. Having defined that, the direction cosines of this member you can define as the direction cosine L is defined as xk minus xj divided by L, where L is the length of the member, and other direction cosine you can define as yk minus yk by L, and this L is nothing but square root of xk minus xj whole square plus yk minus yj whole square. Having defined the near and far end of the member with reference to a global system of global axis chosen, we can find the element geometrical properties like that its direction cosines, its length, everything.
So the coordinate is xj, yj, xk, yk then, right sir?
J and k, near and far end. So xk,
yk.
X, this of course I can write it as, instead of x2, I can call it as xk, yk. This I can call it as xk, yk. These are the coordinates. Just take it as 1 and 2. So instead of 1 and 2, I will use j and k. Let us use it. So these member properties we have to determine. First, the joint information. We have to select a global coordinate. With respect to global coordinate, joint information we have to find out, that is the coordinates of all the joints. We have to evaluate, then find the element geometrical properties, its direction, cosines, length, everything. Having known this, we have to generate the member stiffness matrix locally. Since it is having 2 degrees of freedom, I told, because it's a line member, at the two ends we have only axial force and axial displacement. Like these 2 degrees of freedom, size of the stiffness matrix has to be 2 by 2. We will follow the same fundamental procedure for evaluating the member stiffness matrix. How to evaluate the member stiffness matrix? We have to give unit displacement in the direction of one of the coordinate, one coordinate at a time, fixing the other coordinate. That means you are not allowing any displacement at the other coordinate. That means first I will allow unit displacement in the direction of the coordinate 1, fixing the other coordinate, that is D2, I will make it 0. Then the force required to cause this particular unit displacement I will evaluate, and the force, and I will assume that AE is the axial rigidity, L is the length of the member having determined, and this force required is given by AE by L. Because from fundamentals of strength of materials, we have derived that the displacement at the end of a bar due to a load P is given by PL by AE. If you make this delta as 1, then the force required will be AE by L. Using that simple strength of material formula, I have found out the stiffness. This stiffness might be element. We can call it as K11 because this is the force in the direction of 1 when unit displacement is given at 1 itself. And here, that is force developed. Since it is fixed here, this should be in equilibrium. This force should be equal and opposite to this. So this will be minus AE by L. Then only it is in equilibrium axially. So this force we call it as K2. That's the force developed in the direction of coordinate 2 due to unit displacement at 1. That means since this I told, since there are 2 degrees of freedom, the size of stiffness matrix will be 2 by 2, that is K11, K21, K12, K21, K22. These are the elements of the stiffness matrix. These first column I can generate by giving unit displacement. Then I can give unit displacement in the direction of the coordinate 2. In the direction of coordinate 2, you can give unit displacement keeping coordinate direction 1, 0. D1 equals 0, D2 is equal to 1, you can give it. Then again on same lines, the force required here, it is AE by L, and this force we are calling it as K22 because it is the force due to unit displacement at 1. Here for equilibrium it should be equal and opposite, so I will write it minus AE by L in this direction. This should be in the opposite direction. This is K12. So these elements have been determined like this from the fundamental definition of stiffness matrix, which you have already done in frame problem. Given unit displacement 1 at a time along the coordinates chosen, along the degrees of freedom chosen, keeping each time the other coordinates 0, then evaluate the forces. So therefore this K, which we call it as the member stiffness matrix, this is with respect to local coordinates, mind it. So this Km is AE by L minus AE by L minus AE by L plus AE by L. K11 is AE by L, K21 minus AE by L, K12 is minus AE by L, K22 AE by L. Or this I can write it as AE by L 1 minus 1 minus 1 1. This is the element member stiffness matrix. This you have to remember first. What is the element stiffness matrix, which I was telling in the beginning? you have to determine the member properties, direction, cosines, length, stiffness matrix of that element with respect to local coordinates. Then we have to determine the global stiffness matrix. For our analysis purpose, loads and all will be in the global direction. Stiffness matrix also should be in the global direction. Then only we can use that force displacement relationship for finding global displacement. So now we will go for that particular aspect. That is, we derive an expression for global stiffness matrix as well as a local and global displacement relationship. The same element, and of course here I will call the displacement as d1, here displacement as d2, and the member displacement small dm is always this d1, d2, dm1 and dm2. That is the member displacement. Now we will try to find a relationship between this member displacement in terms of global displacement. That is called the transformation matrix. It's a very simple determination, simple step of arriving at the relationship. Now I will take the same element, that is plain Truss element, in global coordinates. The same Jn, Kn, I element having same axial rigidity, length L, having same L and M, other direction cosines, we will take it like that. But in the global coordinates, let us determine the element properties. So here global coordinate means at this end I should have a displacement parallel to x-axis. This displacement I will call it as uj, and this displacement as vj. There will be two displacements here. Here also there will be two displacements, j, that is u, k and vk. Two displacements will be there. That means you have 4 degrees of freedom. Here you have only two displacements, d1 and d2, whereas here we have 4 displacement in global coordinate for the same Truss element. This is the major change between element property in local coordinate and global coordinate. When you have 4 displacements here along these coordinates which are taken as the positive direction, so here the global displacements are uj, vj, uk, vk. This is that. Here it is only d1, d2. Here it is uj, vj, vj. I have to find out the relationship between this local displacement versus global displacement. That you can easily do it. So we have this dm1, I can write it as uj l plus vj m. Then check, because this is theta. If I take, then cosine theta is your l. This uj, if you resolve like this, it will be uj cos theta. Uj cos theta means it is uj l. Similarly, vj, this will be 90 minus theta. So the component along dm1 direction of vj will be vj cosine of 90 minus theta, that is vj sin theta, that is nothing but vj m. If this is understood, there is nothing much. Then again, on same lines, dm2 also you can write it as uk l plus vk m. That's a simple relationship, just resolution of the displacements. uj will resolve along the axis, member axis. uj into cosine theta, that is ujl, vj sin theta, that is vjm. On same lines here, dm2 is uk l vk m. This I can write it in matrix notation, in matrix form as like this: L, M, 0, 0, 0, 0, L, M and Uj, Vj, Uk, Vk. This is the matrix form of this equation. You can see dm1 is equal to Luj plus Mbj 0, 0. That is same as this. Similarly, dm2 is 0 Uj, 0 Vj, Ukl, Vkm. This equation you can write it in matrix form like this. Or this you can say this is member end displacement in local coordinates. This I will call it as transformation matrix. This is your global displacement. So this is the relationship between local displacement and global displacement. This is called as transformation matrix, which transforms these global displacements to local or vice versa. So this is another basic concept you have to remember in this element approach. How to find the element property, that's basically member stiffness matrix, how to determine this global and local displacement, relationship between global displacement to local, because I was telling in the actual analysis, first we determine the global displacement due to global load, after determining the global stiffness matrix. Then, after knowing that, we will find the element displacement, then we use the relationship force in the members is equal to Km into dm. That's all the basic principle of this element approach of analysis. So this is one thing you have to remember. Then the global stiffness matrix, that is matrix with respect to these displacements. Here stiffness matrix with respect to local displacements I have determined. Here the matrix in this global stiffness matrix has to be a 4 by 4 matrix. It is not 2 by 2. Because here there are 4 degrees of freedom, it has to be a 4 by 4 matrix that we have to determine. That's another important basic concept. This you can straight away remember, this global stiffness matrix is given by the formula T transpose into member stiffness matrix into T. That's all. That formula, of course, is called Cassegrain principle. Of course, let us not go much into the detail about the derivation of the formula. It is finite element approach. Let us not bother about that. Just remember, the global stiffness matrix can be determined by using the local member stiffness matrix, having determined this relationship between global and local displacements. That's all. So this, if you do simplify, this T is nothing but Lm 0, 0, 0, 0, Lm. That is transpose of this column and row. I will change it into column, that's all. This Tt, Km I have derived, that is A by N, 1 minus 1 minus 1, 1. That is Km. And T, of course, is this. L, M, 0, 0, 0, 0, L, M. You can multiply these two first because it is 2 by 2. This is 2 by 4. If you multiply, you get 2 by 4. Then you can multiply the 2 by 4 resulting matrix with this 4 by 2. 2 by 4 into 4 by 2. 2 by 4. This is 4 by 2. This is 2 by 4. You will get resultant matrix of 4 by 4. That is your stiffness matrix. 4 by 4 matrix corresponds to this Uj, Vj, Uk, Vk. This, if you simplify, this is Lm 0, 0, 0, 0, Lm. This is A by N. So this is L. This is 0. This is M. Then 0 minus L. 0 minus L. 0 minus M. Then minus L. Then 0. Then minus M. 0. Then 0 L. 0, M. This is the 2 by 4 resulting matrix. So again, this 2 by 4, you can multiply by 4 by 2 matrix, you will get this 4 by 4 global matrix, global stiffness matrix. So this is L into L, L square, 0 into minus L, 0. So this is L square, this is Lm, then this is minus L square, then this is minus Lm. So it has to be symmetric and I will do it. This is Lm, 0, this is M square, and this is minus Lm, minus M square. Then this row, 0, minus L square, this is minus Lm, then this is L square, this is Lm. Then lastly, this is minus Lm, second, a minus M square, this is Lm, and lastly M square. This is your global stiffness matrix, which for a typical Truss element. This is member stiffness matrix, that is global stiffness matrix with same element properties, nothing I have changed. Same L, same M, whatever we have defined with respect to the member. Here it is length and everything. So knowing this, we can work problem. So this much basic concept you should know prior to your Truss analysis by element approach. Element approach means coordinates you have to remember, local coordinate, global coordinate, what are the degrees of freedom with respect to local coordinates, with respect to global coordinates, then how to generate Km as well as global stiffness matrix. Now we can remember purely this global stiffness matrix is in terms of element properties, L and M, direction cosines of the member, A axial rigidity, and this is L, length of the member, which is again geometric property, coordinates, nothing other than that, purely geometrical properties of the member. So knowing this information, we have to work problem on a Truss element. This is element approach. Same thing we can do even for beam problem also, but that we have explained altogether in a different procedure, that is system approach. Now we will take up an example straight away for the Truss problem and solve it. We will take an example.